Hello, Mom over here, and welcome to a short video covering the last of the four subsystems, the geosphere. Now, what is the difference between the term lithosphere and geosphere? There are references which uses the lithosphere to refer to the solid upper part of the earth. So meaning the earth's crust and the uppermost mantle. So for clarification, we're going to use the term lithosphere to refer to the outermost layer of our planet and pretty much the part where humans and other living things interact with. The term geosphere, however, is more complete because it also consists of the crust, the mantle, and the core. So today we're going to talk about more about the characteristic of each layer of the geosphere. So as stated here on the left of our slide, there are three major layers of the geosphere: the dense metallic core made up of the inner and outer core. We have the rocky mantle, and finally the surface crust, where all the other spheres also interact. Now, in terms of the components of the surface crust, this is very reliable information since we can easily get samples from the surface crust itself. So in terms of the crust's characteristic, this is the thinnest of all the layers, and it's considered as cold, thin, brittle, and the outer shell of the whole geosphere. And it's so thin that it's only 1% or less than 1% of the Earth's mass. So as you can see here stated, 75% of this layer contains oxygen and silicon. Now there are two types of crust, not the pizza crust, but the Earth's crust. So the oceanic crust and the continental crust. So as you can see from our image here, the ones under the oceans are called the oceanic crust, while those that are focusing on land are called the continental crust. So as you can see, comparing it side by side, oceanic crusts are usually thinner and but thin since there is a lot of water compressing it from the top. So pressure that is compressing the oceanic crust makes it dense and thin. On the other hand, you have the continental crust, which is thicker but is not as dense as the oceanic crust. This is where you find the other landforms like mountain ranges, volcanoes, valleys, plateaus, and the like. On the next slide, let's observe the layers of the structure of our Earth. So the thinnest of all, as mentioned, is the crust. We only have 8 to 40 kilometers from the surface. And you have the mantle, which further extends up until 2,900 kilometers from the surface. So we know that the crust itself is just made up of rocky earth, but once we go lower, the layers are not as stable as the outer cold, brittle crust. For example, the asthenosphere is a term used for the upper mantle and the crust, which is interacting, and because of the excess heat, the upper mantle becomes malleable. So it starts to move around, which pretty much results to the tectonic plates and the volcanic activities here on top of our planet. So that's the crust and the mantle. Now, if we go down lower, the sort of molten material now becomes liquid. That's the component or the characteristic of the outer core that is 2,250 kilometers from the surface. And finally, at the inner core, or sorry, 2,250 kilometers thick rather, and then the inner core, we expect it's only 1,300 kilometers, and we know this is solid, this is metallic and solid material. Now, I think from the previous slide or from the previous page of our interactive book, you have read that we have never reached the mantle. So there are no artificial points or human expeditions that have even reached the mantle. So how do we know that all of this is true if we have never measured or taken samples per se of the different layers? So, how did scientists figure out the mass and density of Earth itself if we cannot measure it directly? Well, we have derived these information through physics. So, as you know, we are already aware of gravity and how it works. For example, the higher the mass, the higher the force of gravity in between. So, if we know the constant of gravity's force or gravitational force, then we can already derive the mass of the Earth. So from that logic, the Earth's mass is computed to be 6.10, or rather 6.0 times 10 raised to 24 kilograms. Then you take the speed of Earth traveling through space relative to other objects in our space, for example, the moon, then you can derive the density of Earth. Since we already know the mass, we can measure the speed or velocity, then the Earth's density is equal to 5.52 tons per cubic meter. Now, the only way that this computation makes sense if if the material inside the Earth is much denser than the rocky material outside. Because if the rocky material outside is constant all throughout our planet, then our density should have been much lighter, around 3 tons per cubic meter only. But in reality, we have 5.52, so we can tell that there is most likely heavy material within the Earth. Now, we Now, we don't only rely on derivations of physics in order to figure out what's the material inside the planet. We use additional information gathered from seismic waves. So, for those who are not aware, seismic waves are vibrations from large earthquakes, and they travel from huge or through huge locations. For example, here at the very top of our graph, the epicenter or the source of the earthquake, these seismic waves can travel to different points of our planet, and depending on their pattern and frequency, we can tell how fast and slow they travel, and from there we can see what type of material is within our planet. Right, let's move to a more detailed picture. So again, we have here the epicenter, the source of the earthquake, and each earthquake can produce two types of waves, the P waves and the S waves. So again, these are seismic waves. The P waves are different between the S waves because they have a different pattern. So P waves behave like broken lines, straight broken lines, while S waves behave like waves like um shearing typical shearing waves. Now, whenever they pass through different forms of matter, they also behave differently. For example, P waves can pass through, so the P waves are indicated by yellow. P waves pass through liquid. However, they sort of divert. Okay, again, P waves pass through liquid, but they divert or they sort of reflect or deflect a bit compared to their original pattern. While on the other hand, S waves do not pass through liquid at all. So as you can see here on our diagram, we have the epicenter. So these waves are received through different seismometers located in different parts of our planet. Now, sometimes we can easily get complete P and S waves, especially if the measurement is just close to the epicenter. But if there are instances wherein the seismic waves has to pass through the part of the core, sometimes the results varies. For example, the focusing on the S waves no longer make it to the other side because it is blocked by the liquid outer core. So that's the reason why we know that the outer core is liquid. That's because S waves fail to travel back. On the other hand, the P waves can pass through liquid, but they behave differently. So these different behaviors will be reflected on the seismometers once it is received on the other side of the planet. Furthermore, since the P waves deflected as a reaction to going through liquids, there are shadow zones where no direct P waves are received. But again, that is how we tell that the materials within our planet are quite different, because we have the measurement and predictions of how P waves, S waves, and basically seismic waves react and pattern in different materials. All right, so that's pretty much everything that you should know about the introduction to Geosphere. If you have any questions, please let me know. Thank you.